On our program this week, the main principles of ecology, a meeting with Gαία, and a city stroll. Nowadays, ecological problems have no boundaries. Acid rain, global warming, depletion of the ozone layer, all pose a global threat. The alarm has been raised. The objective, to save the planet and the life it sustains before it's too late. Before becoming the household word we now equate with environmental issues, greening and recycling, ecology is primarily a science. It involves the study of relationships between organisms and their environments. The environment has a major influence on living organisms. Temperature is one of its determining factors. For instance, in northern regions, winter subjects all organisms to very harsh living conditions. Abiotic environment is what ecologists call the non-living factors which condition the living environment. However, living organisms do more than inhabit an environment. By interacting with it, they also modify it. Take the beaver, for example. When beavers build a dam on a waterway, the flooding they cause considerably disrupts their environment. They in fact create a new environment, the swamp, which in turn gives rise to new vegetation consisting of aquatic plants such as water lilies and a new wildlife such as frogs and newts. The various plant and animal species that share the same beaver pond form what is known as a biotic community. All the living species that compose it interact with each other. Of the many relationships linking various organisms together, the most fundamental are based on food. These relationships can be described as a food web made up of numerous food chains. Let's take the example of a deciduous forest. At the base of the food web are the plants. They act as producers. They are able to trap sunlight and to store it in the form of chemical energy. Herbivores, like the groundhog, come next in the chain. They are the consumers. They convert only 10% of the energy stored in plant tissue into animal tissue. Then come the predators, the fox or the wolf, for example. They too only store 10% of all the chemical energy they consume. That loss of energy from one step to the next restricts the length of food chains, and there are few indeed that consist of more than 4 steps. Beyond that number, there would not be enough energy left to support a population of predators. A biotic community and its abiotic environment form an ecosystem. An ecosystem can be a forest, a lake, or even an ocean. An ecosystem is the result of a more or less rapid evolution in time. Generally, that evolution occurs in successive stages. Such a succession can be observed on the site of a forest destroyed by fire. The first plants to recolonize the soil of such a forest are what are known as pioneer species. They are mainly herbaceous plants, such as goldenrod. Able to grow in soils with little humus, these plants proliferate at a rapid rate until they completely dominate the landscape. They regenerate the soil and help make it fertile again. But such plants are victims of their own productivity. By renewing the soil's fertility, they also make it fertile for species other than themselves. They are succeeded by shrubs, for instance, such as bramble, raspberry, poison ivy, which, more vigorous and demanding, take over the site, edging out the pioneer species by competition. Gradually, bushes such as plum and cherry trees and poplars appear and dominate the area. At each new stage, the plants are larger and take a longer time to grow. That's why every intermediate stage in the succession is longer than the previous one. Finally, the first trees make their appearance. These trees, which include the birch or the trembling aspen, are greedy for light. They soon form a high forest which casts so much shade that even their own sprouts cannot grow for lack of light. So these trees die without leaving descendants. They gradually make room for species that can tolerate shade, such as maple and oak trees. These species are typical of mature forests. The vegetative succession then reaches a state of stability called climax. The young oak and maple trees growing in the shade of their elders take their place as the old trees die off. The forest therefore remains unchanged, as long as no disaster befalls it. Of all the ecosystems on this planet, a forest in climax is perhaps one of the most majestic. That's why philosophical and aesthetic considerations can, in this respect, be useful in conveying ecological science, making us aware of the incalculable value of our forests. Some scientists believe the Earth is a living entity. They call that entity Gaia. Guided by the wisdom of her eons of time and space, Gaia watches over her treasure, life, under the benevolent eye of her accomplice, the sun. $3.5 billion years ago, our sun was still just an immature young star and radiated 25% less heat than it does today. And yet at that time, the temperature on planet Earth was conducive to the emergence of life. Since that time, eons ago, the sun has gradually warmed up. We might have expected the heat at the Earth's surface to have become unbearable, but this is not the case. Surface temperature has always remained favorable for life. According to English scientist James Lovelock, this did not happen by chance. Life itself ensured an environment favorable for its own development. For Lovelock, living organisms, the Earth's crust, the oceans, and the atmosphere all form one whole. They are an integral part of an entity which behaves like a living being. Lovelock named this entity Gaia for the ancient Greeks' concept of the goddess Earth. According to Lovelock's hypothesis, Gaia is able to control her temperature like any warm-blooded animal. To illustrate this ability, he developed a simplified model of Gaia called Daisy World. Daisy World is a planet similar to ours, which revolves around a sun, a twin to our own sun. As its name suggests, Daisy World is populated solely by daisies, ranging in shade from white to black. The daisies will only grow at temperatures ranging between 5 and 40 degrees Celsius. During the first season, Daisy World's sun was fairly cool. Only the equatorial sun was warm enough to support life. Daisies of all shades blossom there. However, the dark shades are able to absorb a greater amount of sunlight than the light shades. In areas where the black daisies grew in large numbers, they created a microclimate in which the temperature was slightly above 5 degrees Celsius. By contrast, the white daisies reflect much of the solar radiation. In the sites dominated by the white daisies, the temperature fell below the critical 5 degrees Celsius mark, causing many of them to die. The dark-colored daisies quickly proliferated, helping boost the planet's overall temperature. However, soon the daisy world's sun began to produce more heat. At the equator, the temperature rose above 40 degrees Celsius, causing many of the dark-colored daisies to perish. Because they reflect the sun's rays better, the light daisies replaced their dark counterparts, lowering the temperature of daisy world down to a favorable level. The daisy world model shows that fragile daisies can, in theory, regulate the climate of an entire planet. But how does that model apply to our planet? According to Lovelock, the climate of Gaia is controlled, among other things, by the microscopic algae in sea phytoplankton. These algae live just below the surface of the ocean. They release into the atmosphere small particles of a chemical compound called dimethyl sulfide, or DMS. As it rises in the air, the DMS becomes tiny droplets of sulfuric acid. These droplets of sulfuric acid cause water vapor to condense. They would therefore be responsible for the formation of clouds. The more algae there are, the more DMS they produce, and the more clouds build up. However, the more clouds, the more solar radiation they intercept and reflect back out to space. As a result, the planet receives less sunlight, and its average temperature is lower. This drop in temperature and sunlight is unfavorable to the algae's growth. They then release less DMS into the atmosphere, which slows down the rate of cloud formation and triggers a warming cycle. When the sunlight and temperature conditions become favorable again, the algae begins to thrive anew, producing more DMS, which increases cloud formation, and so on. Until now, it was believed that living organisms simply adapted to the conditions they were subjected to. Lovelock claims the reverse. As he sees it, living organisms are able to regulate their own favorable environment. That is why Gaia is so healthy 3,500 million years after life first appeared. As a matter of fact, Lovelock is not worried about Gaia's health. In his view, even a global warming caused by human activities could easily be offset by Gaia's thermostat. On a planetary scale, any such warming would be the equivalent of a spiking fever. However, were her health to seriously decline, Gaia might react violently to rid herself of the site of the infection. Lovelock is concerned that under such circumstances, Gaia might treat herself in a way that would be favorable to the biosphere as a whole, but harmful to the human species. According to Lovelock, if man does not stop undermining Gaia's health, he may well get a taste of her medicine. To avoid the wrath of Mother Earth, we must learn to curb the damage we inflict on the environment, like we've been trying to prevent our cities from encroaching on neighboring ecosystems. There is nothing quite so unnatural as the wholly man-made environments called cities. And yet an urban environment functions much the same as a natural ecosystem. Like any ecosystem, a city is a place where there occurs a continuous exchange of energy and matter. That exchange maintains the life of the organisms which inhabit it. Let's now step into a forest. It is the sun that supplies the energy the forest needs to live. Trapped by the plants, sunlight is stored through photosynthesis in the form of chemical compounds such as glucose. These compounds are stored in the plant's tissues, Part of that chemical energy then becomes available to the herbivorous animals, which feed on plant life. Then come the predators, which feed on the herbivorous animals. The operation of a city is also based on a supply of food energy. However, in an urban ecosystem, trees and other plants are scarce and play a mainly decorative role. Cities have to import foods from neighboring ecosystems, such as orchards and cultivated lands. In a city, most of the energy is consumed by non-living infrastructures, such as vehicles, buildings, and factories. That energy is supplied by fossil fuels, such as oil and natural gas, as well as electricity. Cities which have to import that energy are therefore totally dependent on outside energy sources. In all natural ecosystems, the plants and animals produce waste. This waste in turn provides a whole community of organisms living in the soil, such as beetles of cicada larvae, with the energy they require. Their role is to recycle part of the organic matter, which the plants will then reuse via their roots. Naturally, the daily activities of a city's inhabitants also produce waste. But the recycling of the residues of human consumption is still in its early stages. The most common solution is to bury the waste in landfills or burn it in incinerators, which are sometimes located in the center of the city. The organisms in all ecosystems modify their environment. The climate, for instance. By retaining part of the heat at the surface and in the air, plants maintain a sort of thermal covering around themselves. The forest also generates its own microclimate, different than any in the immediate vicinity. Cities, too, have their own microclimates. The engines used in its vehicles and industries, together with the living organisms it houses, let off a good deal of heat. Their buildings and roads made of concrete and asphalt soak up that heat as well as the sun's. In addition, many polluting gases, such as carbon dioxide, trap some of that heat. As a result, pockets of heat form above the cities. This is particularly true at nightfall, when the city buildings and highway facilities release the day's pent-up heat. Temperatures at night can be 6 to 8 degrees Celsius higher than temperatures in the adjacent countryside. The numerous buildings in a city have another effect on the climate. They act as windbreakers. Obstructed by the high-rises, the wind has no alternative but to sweep through the narrow streets, sometimes quite violently. As it does, however, it loses much of its energy. That's why fresh air seldom succeeds in renewing a city's stale air, and therefore its distinct climate and smog tends to be maintained. All ecosystems are the result of an evolution. Take the example of an ancient forest destroyed by fire. First, grasses take over the land. But soon, shrubbery, finding conditions suitable for growth, overcomes the grasses. The shrubs will in turn be succeeded by trees, which will form a renewed forest. The forest will eventually reach a state of stability, known as climax, at which time it is balanced with its environment. In many cases, cities undergo a similar evolution. Initially, the founding members of a community gather around a center, the public square. They establish their living quarters around that center. Gradually, commercial buildings replace them, forcing the urbanites to move out to suburban zones. After they have reached their peak, the city centers deteriorate to become what we call inner cities. Both the business and residential districts relocate in the more dynamic adjacent areas. Eventually, urban sprawl will threaten the very vitality of a city. If we were more respectful of the principles of ecology, we might be more successful in our attempts to restore the quality of urban life. The ecology does not only involve our relationship with the environment, but our relationships between ourselves as well. If we want to meet the ecological challenges of the 21st century, we will have to rethink our political and economic systems.